Okay, so thank you, Professor Kester, for inviting me. This is very nice. It's a pleasure to be here. I have visited University of Minnesota before in 2012. Maybe it was 2013, but it was February, so it was a little bit less pleasant. It's very nice right now, actually. Last night I was walking around a little bit when I came back from the airport, and it was actually significantly warmer than the Bay Area, at least at night. Okay, so I'm with the Electrical Engineering Department at Stanford and the Precourt Institute for Energy. We have a website, poplab.stanford.edu, if you want to look up some of our papers or other online resources and so on. So mostly I will speak about thermal and related properties of 2D materials and devices. Related, as you'll see, means some lattice properties, some thermoelectrics, a few things in the context of devices, essentially connecting to some of the earlier talks today. Okay, so I like to show this slide at the beginning of my talks pretty frequently. I think this is kind of a whimsical slide I found on the internet about 10 years ago. That's basically an egg cooking on a computer processor. This was actually done in 2005. And if you look on this plot on the left up here, this is the power density of CPUs as a function of year for the last 20 years or so, right? And so what you can see is that in the last 10 years or so, we've been pretty much entirely limited by power, right? The power has actually been limited. We've essentially been limited by heat and power constraints. And I like this picture not only because it drives home the fact that you can cook an egg on a computer processor, but also the fact that this was actually taken in 2005, which is pretty much when this trend of power increase, by increasing the frequency, essentially stopped. So we've been pretty much in the constant power regime for commercial processors, at most about 100 watts per square centimeter, and typically less, of course, for Atom, ARM, and other kind of mobile processors. At the other end of the power spectrum, and I'm not going to talk about data centers today, but the other end of the power spectrum are data centers. And here's some numbers about data centers in the US. These are very large numbers, by the way. These are gigawatts. So if you look over the last 10 years or so, 15 years actually, data center power usage in the US has been doubling about every 5 years. Okay, we've gone from about 3 gigawatts all the way to about 10, 11 gigawatts today. About half of that is used for cooling, actually. So not all of it is used for computing, right? Worldwide, I am told by people who study these things that the data centers in the whole world are about 30 gigawatts. And again, like I said, these are very large numbers. And I'm more used to working with nanojoules and femtowatts or femtojoules and nanowatts, those kinds of numbers. So I looked it up. A gigawatt is the power generated by one large nuclear power plant, and 12 gigawatts is the electricity used by the entire country of Argentina, right? So the data centers in the US today are using as much electricity as the country of Argentina, just to kind of put things into perspective. Okay, so we're obviously an academic group. We don't work necessarily on data centers, although I find these things interesting. The way I like to think about what we do is sort of looking at two sides of the same coin. On one thing, we sort of wonder where the power comes from and what we can do about that. And on the other side, which is obviously more the topic of this talk, is how to harvest and manage the heat that is generated in electronics anyway. Of course, we're academics, so we're always interested in fundamentals, but we're engineers, so we also want to make sure that what we do is connected to practical applications. And so, really quickly moving into materials, the materials that my group typically looks at are shown over here. I like to group them by dimensionality, so they range from 0D all the way to what I call plus 2D. These are 3D materials that have 2 extra degrees of freedom in terms of phase change, metal insulating, essentially, materials. But the subject of today's talk is 2D materials, and here's a bunch of them. And of course, these require no introduction, especially after the 2 really nice talks this morning. I just want to mention that one thing that sort of sometimes is on our mind is that the atomic dimensions of especially 1D and 2D materials automatically in some way address some size scaling issues which Moore's law obviously has been driving us towards for many, many decades now. Okay, so as an outline of my talk, here's essentially what I'll be talking about for the next 40 minutes or so. Atomic structure, energy bands and phonons. Some electrothermal effects in the context of devices, right? So I'll be trying to tie into the earlier talk. And then looking at some of the basics, more fundamentals of thermal transport, and also trying to look ahead what these might mean from a functional point of view for these materials. So this is the first part of my talk. Okay, I think you've seen this before as well, so just kind of a recap. The atomic lattice structure of some 2D materials, graphene, of course, is shown there, boron nitride, silicene, these TMDs, transitional metal dichalcogenides, black phosphorus, and isotropic, of course, right? So these things are typically 2H or 1T, sometimes 1T prime, which is a distorted 1T lattice. There's also phase change properties of these TMDs between the 2H semiconducting state and the 1T or 1T prime metallic state. These things can be induced, for example, in molybdenum telluride by temperature, strain, or by lithium intercalation, as people have shown, actually also in MOS2. This is really just a tribute to Professor Rajan's talk this morning, or rather my tribute to his talk. Then, back maybe 10 years ago or so, right, when this whole field kind of started, we were working with a whole bunch of Scotch tape and getting sort of random, 10 micron at best pieces of junk, that we would make devices on. And today, of course, we have large-scale, mostly CVD methods, at least in my group. This is graphene, of course, on 4-inch sort of copper foils, boron nitride, molybdenum sulfide, and then some of the weirder TMDs that I'll talk about a little bit later. In fact, just kind of to highlight some of the growth that is happening at Stanford, this is more of a Stanford-specific slide. This is a collaboration with Philip Wong, Yoshio Nishi, and Ian Fisher in the physics department. Basically, the capabilities that we have right now at Stanford, what we're playing with are these 4-inch graphene growth system for circuit applications. That's where we're driving that. We have a 2-inch boron nitride growth system, and that's coming online nicely. We're really looking forward to actually making devices on CVD-grown boron nitride monolayer, self-limiting stuff. And then I think like a lot of people, we've been able to grow monolayer molybdenum sulfide by CVD with properties almost approaching those of the exfoliated stuff. And then we have another thing called chemical vapor transport. And here we don't actually grow monolayers. We grow multi-layer, sort of thick millimeter scale films. And then we still have to rely on the Scotch tape to essentially peel these apart and do individual devices. But these are some of what I call the weirder TMDs. These are molybdenum telluride, which is a phase change material, zirconium selenide, hafnium selenide, which have lower band gaps among the TMDs, and then tungsten telluride, which shows up as a 1T prime metallic phase every time we grow it. And it's kind of an interesting material by itself. Probably the only 2D material other than graphene that we've worked with. Okay. This is, how do you look at 2D materials? I've sort of always scratched my head trying to, kind of put together the zoo of materials. This is a slide put together by Michael Mleczko in my lab. He basically likes to look at these things as, in terms of band gap, for instance, ranging from obviously, very small band gaps, smaller band gaps, zero band gap to small band gaps, low power CMOS is somewhere in here. And then we have all these other TMDs with band gaps between 1 and 2 EV. And then, of course, we have the insulators and so on towards the right. I think you all know this already, especially from Professor Zhu's presentation. But low band gap but high mobility, you could go for high-speed or RF applications. Medium band gap, of course, low power CMOS, and then larger band gap for power devices, perhaps. But maybe a more whimsical way to look at 2D materials, also put together by Michael Mleczko in my lab, is to basically look at them, on a scale from stable to complete pain in the neck. We know that boron nitride and graphene are pretty stable. You exfoliate or you grow these things, and that you can go back, and the samples are fine after months. Black phosphorus, hours to minutes degradation. And then some of the silicene, stannine stuff that we've seen seems to be almost instantly degraded. And so this is, I think this is a little bit, the coloring scheme is not exactly what's on my laptop screen, but you can imagine the color here corresponds to the color down here. So, if you go by the metal and if you go by the chalcogen, like that, basically molybdenum sulfide is probably the most stable among these things. And then these zirconium tellurides or hafnium tellurides and so on going like this. Our experience seems to be the least stable. And this sort of goes down, the periodic table in terms of the chalcogen column, I'm sorry. And this seems to roughly scale with a metal reactivity, especially the metal reactivity with oxygen. That's what we kind of seem to see. Although it's a little bit harder for me to form sort of an intuitive picture of what's happening there. And again, take this with a big grain of salt because this is quite qualitative. But here's a nice picture from the literature. This is molybdenum telluride. I don't know if you can see this in the back. Over a couple of days, monolayer molybdenum telluride essentially disappears, right? And we see this as well. So whenever we work with molybdenum telluride in our lab, we try to do the measurements like the same day, right? But if you do them the same day, it's kind of okay. Tungsten telluride, a little bit more tricky to work with. This is work, actually Michael's work in my group. We've done XPS, for instance, after a couple of days, and we see tellurium oxide peaks forming. So it's very, very clear what's happening over here. This is the exposed, unencapsulated tungsten telluride. If you cap it with aluminum oxide, it seems to be stable, at least for a week. So aluminum oxide, we found, if you work in a glove box and then you immediately cap it with aluminum oxide, it seems to actually be relatively stable, so then it actually enables you to do something with it. But otherwise, tungsten telluride is basically, it's quite difficult. Tungsten tellurium, you can see, would be quite difficult to work with. Okay. Just a couple of words about electronic band structure. My talk is really more about phonons than electrons anyway, but a couple of words on electronic band structure. I'm sure you're familiar with the one in graphene, the K and K prime degeneracy, the nice, beautiful linear bands, at least around the tips of the Dirac cones. And then these are the energy bands in the MX2, transitional metal dichalcogenides. And the K bands are 2x degenerate. The Q valley, I'm sorry, is 6x degenerate. I should say K valley, and the Q valley is 6x degenerate. The Q valley, sometimes people call this Q. I've seen it mislabeled sigma. I think that's actually an error. I would say it's basically this is what's along the T line inside the Brillouin zone of the TMDs. I've also seen it labeled as I, actually. And I'm actually not sure why some people call it Q, some people call it I. But I'm pretty confident sigma is actually not correct because sigma comes from a different type of Brillouin zone arrangement. Some of the questions that remain kind of open are, what are these energy valley spacings, for instance, right? And that's why I highlighted these things. For different materials, different layers, and so on. What is their dependence on strain? In fact, this is some other nice computational work. Here, for instance, is molybdenum telluride. Here's molybdenum sulfide. You can see that as you go to monolayer, and I think you all know this, as you go to monolayer, the bands are direct, right? But then if you take these direct band gaps and then you strain them, this is compressive strain, this is tensile strain, you essentially have different shifting of the K and Q valleys, right? And you can end up again with the indirect band gap in monolayer materials. And so, like I said, some of the unknowns that remain, as far as I'm concerned, in these materials are the strain effects on the conduction and valence bands. Phonons. Phonons are the lattice vibrations, right? And you have sort of, there's a cute cartoon here of what these things essentially look like. These are the atomic motions, right? Waves and so on. We have longitudinal phonons, which are essentially these compressive waves, and then you have transverse phonons, which are these shear waves, essentially, right? Here on the right, I'm showing the phonon dispersion of graphene, right? These are the acoustic modes, which essentially carry the heat in the lattice, and these are the optical modes, which, as you can imagine by their name, interact fairly strongly with light, largely because of their large density of states here at 0 K vector, so around the gamma point. This is actually what you pick up as the G mode in graphene. The slope of the bands right here, this is important, is the sound velocity in the material. So no wonder graphene has very, very large thermal conductivity, because essentially the slope of the acoustic phonons, or the velocity of acoustic phonons in graphene, is extremely large. And just for comparison, I can't really overlay two dispersion relations because it's going to look like a mess. But for comparison, the optical phonons in graphene are over here. The silicon optical phonons will be down here somewhere. So you can imagine the silicon bands will actually have significantly lower slope. And also, so you can see where 26 MeV is on this, it's roughly around down here. So that kind of gives you an idea of which phonons are conducting at the most at room temperature, if you can say something like that about bosons, of course. It's not really like a Fermi level, but it kind of gives you an idea. Okay. So having said that, here's a slightly deeper look at the phonon dispersion in graphene. As I mentioned earlier, the velocities for phonons are actually quite large. The longitudinal acoustic modes, about 21 kilometers per second. In silicon, that's 9. The transverse acoustic modes, 14 versus 5. So about a factor of 3 larger phonon velocities than in silicon. What is unusual about 2D materials, and you actually do not see this in 3D materials, are the ZA and ZO modes. And so these are the out-of-plane bending or flexing modes, which, as I'll show in a moment, are actually quite important for heat capacity, right? Because the density of states in these things is actually quite high, both in the ZA as well as the ZO modes. And the ZA mode actually has an effect on thermal conductivity as well. This wasn't originally recognized for graphene, but it does have an effect on thermal conductivity as well, because these are very highly occupied modes at relatively modest temperatures. Here's the phonon dispersion of other 2D materials. Again, it's very difficult for me to show these sort of side by side, but I tried my best. I know this looks a little bit, this is probably one of my messier slides. So there again, that's graphite. You see the transverse modes. I'm sorry, the flexural modes, ZA and ZO and so on. Here's boron nitride. Notice that the vertical scale is about the same. It deliberately chose the same. This is 200 MeV. That's 200 MeV. So boron nitride is probably the only other material that has phonon modes that keep up with graphene or graphite, right? So again, you automatically expect boron nitride to have very good thermal properties just by looking at the phonon dispersion, right? The one other thing I want to point out, by the way, is this gamma to A thing that shows up. Gamma to A is the out-of-plane component of phonon dispersion, right? Look how small those phonon modes are. So A, those are fully occupied at room temperature, and B, they have incredibly slow, sound velocities, right? Which means, again, just intuitively looking at this, means that the out-of-plane thermal conductivity component of these layered materials is going to be tiny, right? So you can kind of already imagine that these materials are thermally very anisotropic, and I'll show you some numbers for those a little bit later on. Here's MOS2. This is the phonon dispersion MOS2 calculated as well as measured. Again, you see the out-of-plane phonons, same thing. Gamma to A, very, very small group velocities, all thermally occupied at room temperature. Tungsten disulfide, we could not find experimental data, but we do have calculations from one of our collaborators. So you can kind of see, of course, graphite's been a lot more studied, and then sort of this is a little bit less so from the point of view of phonons. But notice the vertical axis, 60 MeV, 60 MeV. These are 200, right? So these are going to have significantly lower phonon energies, the heavier materials, of course. I want to say just one word about heat capacity. Heat capacity is basically, well, it's basically the ability to store heat, right? It's the energy per degree Kelvin per unit, per unit mole, if you will, or per gram or per cubic centimeter, depending which units you prefer. This is where the ZA modes are a little bit interesting. Look, for example, diamond and graphite, right? So here's the density of state, here's the phonon dispersion for diamond, and here's the phonon dispersion for graphite, and the corresponding density of states. You will see that in graphite, at the same temperature as in diamond, you actually have significantly larger density of states than in diamond. That's because of the flexural ZA modes right there, which are these bendy modes with a quadratic phonon dispersion. And so if you actually look at the specific heat for graphite and for diamond, at room temperature, the specific heat in graphene is about 30% higher, or graphene or graphite is 30% higher than in diamond. And then eventually they converge only at temperatures above about 1,000 degrees Kelvin. At really low temperature, there's actually very subtle differences between graphene and graphite heat capacity, but these are temperatures below about 100 degrees Kelvin. And so at room temperature, graphene and graphite essentially have the same heat capacity. At lower temperatures, there's these subtle dispersion differences, because in graphene you actually have a slightly more free out-of-plane flexural modes, whereas graphite, they're a little bit more confined, as you might imagine, right? What else should I say? There's an interesting rule of thumb in the phonon world, which you can look up, for example, in the solid-state physics books like Ittel's. The heat capacity tends to scale as T to the power D over N, and this is for a phonon dispersion, omega going as K to the power N in D dimensions. That's what this funny term means, right? So for instance, in silicon, this would be a linear dispersion, and it's 3D, so it would be T to the power 3, right? But in graphene and in graphite, you actually have some funny exponent terms. And like I said, you really only notice those at really, really low temperature. At sufficiently high temperature, all the heat capacities essentially approach what is known as the classical Dulong-Petit limit. Of course, graphene and diamond really become classical only at temperatures above about 1,000 degrees Kelvin. Okay, that was supposed to be circled there, but that is the same thing. It doesn't matter. Or I already said it. Raman spectroscopy. So Raman spectroscopy is something that obviously I don't have much time to talk about, but it is something that we use quite frequently, not just us, but I think everyone in this community uses quite often because it allows us to probe the phonon modes directly in a way. And I think Professor Zhu already showed this. You have these in-plane modes labeled the E modes, and you have the out-of-plane modes labeled the A modes in some of these TMDs. There's really a wealth of information that can be gained from this. And here's some of my favorite reviews, which I just listed at the bottom of the slides for your convenience. But we can estimate, for example, the thickness of the 2D material, because thickness affects the phonon modes, and there are subtle differences that basically allow us to map this to a number of layers. We can, for instance, study strain, right? So the E mode, the in-plane mode in MOS2 is sensitive to strain, as you might imagine. And also the G peak becomes split in graphene also due to strain. Doping, the out-of-plane mode is sensitive to doping in MOS2, and then the G and 2D modes in graphene are also sensitive to doping. And then defects, of course, the very, very famous deeping in graphene appears only when you have essentially defects. And unfortunately for us, there isn't, to my knowledge, an equivalent mode in MOS2. So it's not as easy to map out your defects by Raman in MOS2. Photoluminescence, perhaps, but not Raman. Okay. So a couple of words about where these thermal effects play a role in devices. And hopefully I can make some bridges with the presentation by Professor Zhu a little bit earlier today. Some work that we did a few years ago now, so almost 5 years ago now actually, was we took some of our earliest graphene transistors and we stuck them underneath an infrared thermal microscope. And frankly, I'll be honest with you, I didn't expect to see anything. I said, graphene's transparent, I'm not going to see anything, right? But we had an infrared thermal imager nearby, and we said, well, let's just see if we see something. And amazingly, we actually saw quite a bit of infrared thermal emission from the graphene channel. Later on, we realized what was actually happening is, yes, graphene is transparent, mostly transparent to infrared, but actually what's happening is the graphene is heating up the silicon channel, the silicon substrate underneath, and we're actually imaging the heating of the silicon substrate, which is this is free carrier emission from the silicon substrate, which is heavily doped. But regardless, the point is you see a huge signature of heating. And this is actually a hotspot that dances around the channel. If you go to our website, you can see a movie of this thing. It dances around the channel depending on the source, drain, and gate voltage that you apply on these transistors. And so just to kind of make a long story short, what we realized is that graphene transistors are ambipolar. And so when you operate them as a unipolar transistor, the hotspot occurs near the source or near the drain, which is pretty much what you expect in like a conventional silicon or gallium arsenide or gallium nitride type transistor. You essentially get a slight carrier depletion near the drain. I wouldn't use the word pinch off because in graphene you never really get real pinch off, right? Because there's no band gap. But you get a slight carrier decrease, right? And so there's a hotspot that forms at the point of minimum carrier density because that's where the maximum field is. And so that roughly corresponds in the IV curves to the saturation regime. But this again looks very, very similar if you're familiar with other 2D semiconductors. With other semiconductors in general. Where graphene is a little bit bizarre is that you can actually inject electrons from one terminal and holes from the other terminal. And so if you do that, it turns out the electron and hole carrier densities arrange themselves in an X. Okay? And this can be calculated using fairly simple computer codes. And so if they form in an X, the electrons and holes, there's going to be a point of minimum carrier density that's actually in the middle of the channel. And that's going to be the point of the hottest, highest electric field, hottest region, and so on. And that's when the hotspot dances to the middle of the channel. And so we see this. And so it's a kind of a nice way to thermally observe the carrier densities inside the channel. That's essentially what is happening over here. We actually put together a model, obviously for that work. That's how we were able to explain it. We took that model one step further a few years later. We took it a step further because I really wanted to look with the model to device dimensions which we couldn't thermally image, right? Imaging things with infrared you can only really do on really, really large devices. Even with Raman, you really need micron scale devices to see anything, right? With the model, you can study something sub-micron, and as long as the physics is right, probably what you're going to get is going to be pretty reasonable. Anyway, one question that I frequently used to get when I was showing the previous slide was, well, if you put a gate on the device, like a top gate, isn't the top gate just going to suck away all the heat, and therefore your device will no longer heat up? Or the other question that I would get, of course, is doesn't graphene have a really high thermal conductivity and carry the heat to the contacts, right? So this actually kind of set out to answer both of those. If you have a gate on top, what happens is the gate is really not a really good heat sink, actually. It turns out the heat still goes to the substrate. The gate itself, you can think of the gate as the egg sitting on the pan. Well, earlier it was an egg on a computer processor, but you can imagine an egg on a pan, right? You put a pan on the stove, you put an egg in it, right? The pan heats up, it heats up the egg to the same temperature, right? But the egg itself is not actually a heat sink, right? However, what the egg does do, or whatever's in the pan, your favorite pasta dish or something like that, what it does do is it actually slows down the rate at which the pan heats up. So there's actually a thermal capacitance component that the gate actually brings in. Not only the gate, but also if you have this encapsulated in some sort of a capping layer like you might have inside a real transistor. So what we realize is that the gate and the capping layers actually affect the transient, not the ultimate temperature of the device for a given power density, but the transient, how the device actually gets there. So we did these transient simulations. The devices have fairly fast thermal transients if they're not capped. But if you put a cap and a gate and so on, then the thermal transients actually slow down quite a bit to the order of hundreds of nanoseconds. Otherwise, they could be tens of nanoseconds or something like that. And by the way, the graphene itself has such a small heat capacity in this case because it's a monolayer that really, even for an uncapped device, most of the heat capacity is the one in the substrate. It's the SiO2 and the silicon substrate that actually takes some time to heat up. Otherwise, the graphene itself would heat up in less than a nanosecond. So it'd be almost instantaneous. To answer the heat dissipation to the contacts part, I guess I don't have a good, it's not really shown over here, but essentially what we found out is that, yes, you can get significant heat sinking to the contacts, but only in devices that are shorter than about half a micron. For any device longer than about half a micron, most of the heat actually goes into the substrate. For short channel devices, of course, the contacts do play a significant dissipation role. And you can kind of see that a little bit in this temperature plot along the channel. This is actually a fairly longer story, but just to make it shorter, we sort of took the same devices that we had earlier and we got rid of the substrate. I like this kind of as an extreme case because by getting rid of the substrate, we said, look, this is going to allow us to study the intrinsically coupled electrical thermal properties. Right now, the heat cannot go into the substrate. Now it really can only go to the contacts. We have a simulator. Great. Let's compare experimental data for high field transport with simulations for high field transport. And what we realized is that essentially comparing, going back and forth between these two, we could actually fit the thermal conductivity of the device, of the graphene, because heat can only go laterally. So in this case, you're really forced to heat sink to the contacts. And we can actually fit the thermal conductivity of the device all the way from about room temperature all the way to the breakdown temperature of these graphene devices, which we estimate to be about 2,000 degrees Kelvin. By the way, this was all done in vacuum, of course. We could also fit for various devices what we thought was the high field drift velocity, and it was something approaching on the order of 3 times 10 to the 7 centimeters per second, which was predicted to be the intrinsic sort of maximum velocity you would get. Okay. I mentioned this model. I don't want to say too much about it except that it's an iterative solution of the charge, continuity, Poisson, and of course the thermal equations. This model is actually available on the NanoHub right now. It's called GFET tool, Graphene FVT Tool. So if you really find this useful, or if you simply don't like the rest of the talk, you're welcome to try it out right now and let me know how it works. More recently, we've also released a slightly more compact model called the Stanford 2D Semiconductor model, S2DS. This is actually specifically aimed at TMDs, right? So this is obviously for graphene simulation. This is for TMD, two-dimensional semiconductor simulation. They're both available on the NanoHub. This one you can run directly in the NanoHub. The other one you have to download, and essentially it's written in Verilog A. But this is a little bit more amenable for circuit simulations, and that's what we're using it for right now. They're both electrothermally coupled and so on. And of course, you can tweak a lot of the parameters by hand. Okay. A little bit more on the on the thermometry side, we were not very happy with the infrared thermal imaging because the resolution is so poor, right? It's microns. It's about a micron or two. Raman spectroscopy, same thing, about half a micron maybe. So we worked with Professor Bill King at UIUC several years ago, and we used an AFM-based method to measure temperature. In this case, we essentially use an AFM tip to measure the thermomechanical expansion of the material itself. In this case, I know this picture is a little bit misleading. This was done by an artist. Please forgive this picture. It's a cool picture, but it's actually misleading because the device itself is covered by a layer of PMMA. So the thin layer of PMMA essentially acts as a thermomechanical expansion layer. So as the graphene or whatever this material is heats up, the PMMA heats up, and then the AFM picks up the thermal expansion of the material, and then you convert that back to temperature. Long story short, we didn't see anything we didn't already know in the channel, so that was good, I guess. The infrared imaging method actually showed us enough of that. But then we zoomed in on the contacts, and when we zoomed in on the contacts, we actually realized that we were seeing not only significant heating in the contacts, but we were also seeing cooling in the contacts if we were reversing the direction of current flow. So when the current flows into the contacts, you get more heating. When the current flows out of the contact, you actually get less heating, just right in the contact. And so these are two effects happening inside the contacts. One of them is what you would expect, which is current crowding. That controls about 2/3 of the temperature in the contacts. And then the other effect is a thermoelectric effect, which was actually really surprising. We saw it experimentally. Our models couldn't even explain it. But we saw it, and then as soon as we put in the thermoelectric effects in graphene, we actually got this, and it worked. And what I find really fascinating is that graphene doesn't even have a very large thermoelectric power, as I'll show a little bit later. So this effect must actually be more pronounced in other 2D materials. We haven't studied it yet, but it's perhaps something that we ought to do, or you ought to do if you are interested. Okay. By the way, same technique can also be applied to study heating at graphene grain boundaries. So here's a juncture of two graphene grains. This is a grain boundary. There's a wrinkle. You can actually see significant heating at the grain boundary. You can see a little bit less heating at the wrinkle. So you can kind of know which one's more resistive, which isn't. And this is actually probably a better picture. You can see here that the AFM tip essentially scans over the graphene covered by a PMMA layer, and that's what's actually causing the thermomechanical expansion, which we can then pick up with the AFM. Okay. A little bit of thermal engineering went into this work. Graphene nanoribbons, we were interested in them for interconnects, of course. And what we realized is that actually by engineering the heat sinking into the contacts by essentially making short channels, so this is not significant engineering, but yes, we realized, yeah, if you make short channels, you can actually get a lot of heat sinking to the contacts. And then if we make thin oxides for the substrate, you can actually get more heat sinking into the substrate. So we were actually able to get significantly increased current densities, basically more than a gigaamp per square centimeter to these graphene nanoribbons. These are actually CVD-grown graphene nanoribbons, so they're not even particularly great for low-field measurements. But actually at high field, they were quite impressive. They were almost as good as carbon nanotubes as far as current density is concerned. And this is basically just kind of a simple example to show that just a little bit of thermal engineering can actually really help you with some of these 2D materials, can help you sink more current, for example. If you sort of engineer the dimensions and the materials around them just a little bit, you can actually get quite a bit of increase in current. Some similar work in MOS2, which we've been pursuing recently. We've been seeing some strange effects at high field and low temperature in MOS2. We see this negative differential conductance, right? The current goes up and then the current comes back down. And of course, us being who we are, we said, well, this clearly must be self-heating, right? We've done this in graphene. Of course, self-heating must play a role in MOS2. But it turns out we weren't able to explain it purely through self-heating. And that's when we started digging a little bit more through the band structure of MOS2. And we realized that there's probably a lot of intervalley scattering that is actually happening between these K and Q values, which I mentioned a little bit earlier. So you can see that if you include heating or if you include two valleys, you can't reproduce the experimental data. But if you include both the valleys and the heating, we're actually able to reproduce the experimental data across a wider range of temperatures and across a wider range of fields, of course, right? Okay, so the last part of my talk is more purely focused not only on the thermal properties and a summary of them, actually, really trying to wrap up, but also looking ahead and seeing what maybe new functionalities we could enable by engineering thermal transfer, besides the ones that I've already shown you, which are fairly simplistic at the device level. So here's a summary. You know, if I were to summarize maybe this talk on one slide, perhaps this is it. The takeaways are that there are some really large in-plane thermal conductivities for graphene and boron nitride, really large, larger than metals, larger than copper, for instance, right? Copper is about 400. These things are about 500 and above at room temperature, of course. But at the same time, as I hinted about 15 minutes ago, the cross-plane thermal conductivities are extremely low, right? This has to do with the very, very weak coupling between layers and the weak van der Waals coupling between the layers and the environment, as you can imagine, right? And there's actually some data from a few years ago showing that tungsten diselenide has actually thermal conductivity, cross-plane, of course, lower than 0.1 watts per meter Kelvin, which is actually lower than some plastics and almost comparable to air, right? So this is kind of, it's very mind-boggling in a way that a material could have such, this is a solid material that has such low thermal conductivity, right, cross-plane. So there's a huge amount of thermal anisotropy pretty much in all layer 2D materials, period. We wrote a little review paper with Air Force Research Labs collaborators. This was more focused on graphene, so we're writing another one right now that's more focused on TMDs. It hasn't come out yet, but some of the figures I'm about to show you are actually from the new paper that we're writing up. And actually, before I move on, I just want to point out that there's been some measurements of thermal power in these TMDs. And people are getting really large numbers. But I want to put those into context because I think there's been a lot of rush to say, hey, you know, these actually have like amazing thermoelectric properties. But really, we should probably put that into context, as I'll show in a moment. So here's a summary. This is a summary from the upcoming review paper, a summary of the thermal conductivity of a whole family of 2D materials. And we absolutely had to split these by in-plane and cross-plane measurements. So you see these are the graphite, suspended, supported, encased, graphene nanoribbons that we've measured. This is the graphene. Boron nitride, pretty good. Notice the vertical axis is logarithmic. This is a huge, huge range for thermal properties. Thermal properties do not, vary like electrical properties. They only vary, you can only really vary them in solids by 3 or 4 orders of magnitude. This is it for pretty much all solids, right? Maybe you can go another order of magnitude lower in really, really disordered things or plastics. The TMDs, black phosphorus, pretty low thermal conductivity. But then if you want really low thermal conductivity, of course, you have to go cross-plane, right? So even graphite has terrible conductivity cross-plane, even boron nitride, some of the TMDs, and so on, right? So again, the take-home message here is this anisotropic thermal nature of 2D materials, right? Very, very low thermal conductivity. By the way, everything I've shown, unless I mention it specifically, everything I show you is room temperature because that's generally where I really kind of inhabit, literally, is I like room temperature. But here's a bit on the temperature dependence of thermal conductivity. So the temperature dependence of thermal conductivity looks basically like an upside down V or upside down U, depending on which letter you like better. And so at low temperature, it scales as the heat capacity, which I already covered, right? It goes, but this is really low temperatures, 10 to 100 Kelvin. So thermal conductivity scales as heat capacity because you have more and more phonon modes which are occupied and so on, right? But then you hit a temperature where you've sort of occupied all the phonon modes that are kind of relevant to occupy. And so then phonon-phonon scattering really starts to come into play. And then you start getting this thermal conductivity that scales as 1 over temperature, right? And so you see this above, about above room temperature, right? In graphite, and pretty much all these materials, nanotubes and so on, right? And this is due basically to what's called Umklapp phonon-phonon scattering, right? And so for most of these materials, 2D materials or otherwise, the peak thermal conductivity actually occurs at some intermediate temperature, depending on the impurity or defect scattering in the sample. But this temperature, you can, if you squint and you're in the back, you can kind of look like peak thermal conductivity is around 100 degrees Kelvin. Not at room temperature. At room temperature, you're already on the downward slope, so to speak, right? But certainly at 100 Kelvin, pretty high thermal conductivity. Actually, even higher, of course. So a couple of words on the Seebeck coefficient. This is, by the way, all at room temperature. So my students, Lily and Elise, went through literature, and they just did this wonderful search of the magnitude of the Seebeck coefficient. This is, by the way, all measured, right? And so you see this amazingly rich data set, which, so far the only way we can really group it is by in-plane and then cross-plane measurements. I think I'm running out of battery. Do you have another one by any chance? Oh, there's a backup?
No, they're just new batteries.
Oh, okay. All right. Okay, that's fine. I'll just use the analog pointer. So anyway, so we just group these by in-plane and then cross-plane measurements, and then there's some bulk measurements here which were actually not mentioned, so I'm not sure. To compare these, the Seebeck coefficient, the magnitude typical for thermoelectrics is in that range, about 100 to 1,000 microvolts per Kelvin. But what I want to remind you, and this is why I want to put this into context, is that the Seebeck coefficient of materials is proportional to the energy difference between the Fermi level and where the electrons or the holes are traveling. So if you have a really undoped material where the Fermi level is in the middle of the gap, the Seebeck coefficient is going to be huge, right? And so these very large values that were measured for MOS2 were actually for relatively clean, undoped samples, right? And so if you remember the ZT formula that I flashed a couple of slides earlier, to actually have good thermoelectrics, not only do you need large Seebeck coefficient, but you also need large electrical conductivity, okay? The problem is that, just to kind of put these pictures into context, some of these very large Seebeck coefficients that were measured, the electrical conductivity was not reported on the same sample, so I don't even know how to summarize this any better than we already did. But B, also, I know from basic physics that the range that we show, some of the largest ends of the range are actually for the least doped samples, right? When you're actually gating them with a Fermi level in the middle of the gap. So those will have really low electrical conductivity. So of course, they're not necessarily the most useful samples. But there's still some trends that emerge. For instance, tin selenide has some interesting thermoelectric properties. For instance, so there's definitely, I think, a lot to be learned here as well. Okay, a couple of words about nanoscale samples. I think a lot of us recognize that devices, transistors, interconnects, and so on. They're sort of, thank you. They're sort of very cool when they're less than a micron in scale, right? If they're bigger than a micron, it's sort of you go to Intel, you give a talk, and they sort of like, what's the point, right? But if it's less than a micron, right, or preferably less than 50 nanometers, and so things are kind of interesting. Plus the physics is also kind of cool. And so what you probably know from resistance, electrical resistance, is that Ohm and Fourier, Ohm's law, holds all the way till you reach the nanoscale, right? But the same thing happens with Fourier as well. So Fourier's thermal laws hold all the way until you reach the nanoscale. But then when you actually get to very small dimensions, you can have quantized resistance, ballistic effects, both electronically as well as thermally, right? In fact, there's some weird math. Macro scale, you take a resistor, you add another resistor, you make it longer, the resistance goes up, right? 1 + 1 = 2. In the nanoscale, if you have two ballistic resistors and you take a ballistic resistor, put it in series with another ballistic resistor, you still have a ballistic resistor. So it's kind of a funny math that 1 + 1 = 1, essentially. That's what that means. When do these things happen? These things happen at dimensions of 10 to 100 nanometers, right? So that's basically when these things are occurring. And I do want to point out the difference between resistance or conductance and conductivity. So if you convert between resistance and conductivity using just that simple equation, in bulk, in the macro scale, of course, conductivity is a constant. But actually in the ballistic regime, and this is a little counterintuitive, in the ballistic regime, the conductivity actually goes to 0. And it scales linearly with the system size. Otherwise, if the conductivity doesn't go to 0, you're not going to obtain a constant conductance, right? And so I remember as a student, the first time I saw this, I said, wait a second, if it's ballistic, shouldn't the conductivity go to infinity? Actually, conductivity goes to 0 because the conductance goes to a constant. So, and the math is right there on the slide. It's very simple, but that's something that I think sometimes perhaps slips through the cracks. And so we looked for these kinds of effects in graphene. Because the conventional wisdom would be that, of course, diamond and graphene are going to have the highest, the best ballistic effects, thermoballistic effects at room temperature, because they're the most thermally conductive. They have the largest phonon mean free paths and so on, right? And we built these test structures, which, this whole project was probably one of the longest projects in my lab because so many things went wrong while we were doing this. But we put heaters, we put thermometers. These are graphene ribbons. Some of these are nanoribbons. Some of them are just ribbons, right? I'm showing one of the nanoribbons here, but we also had much larger ribbons. And the array ensures that we get enough heat flow between the heater and the thermometer. It kind of looks like a thermal transistor, if you will, right? There's a source and a drain, except there's a heater and a thermometer. Again, if there's one take-home message here, it's this boxed red thing, is that we uncovered that the thermal properties of bulk graphite or graphene that I showed you earlier really only apply in samples greater than a micron. If you go in samples less than a micron, you actually can't use the bulk thermal properties I showed you earlier, the thermal conductivity. Why? Because you have these ballistic effects and weird edge scattering effects happening. So essentially, I know this is a really busy slide, so I'll just refer you to this paper from 3 years ago. But to make a long story short, the thermal conductivity becomes a function of length. That's actually a ballistic effect, which you kind of expect just based on what I said earlier. The conductance is starting to become quantized, and therefore the conductivity appears to essentially decrease, right? And so there's a very, very simple model following Mark Lundström's work from Purdue on how to kind of bridge the diffusive and the ballistic regime. And actually that seems to fit the data very, very nicely. And then the other thing is the width dependence. And the width dependence is maybe a little bit more classical in the sense that, yeah, if you have ribbons, they have edges. When you etch these ribbons, the edges are not perfect because we etch these by oxygen plasma, right? And so the thermal conductivity is actually going to decrease as a function of width. And the thermal conductivity falls off at widths less than about 200 nanometers. So when these ribbons are narrower than 200 nanometers, the thermal conductivity drops precipitously as W squared. And then if it's above that, it's actually limited by scattering with the substrate. Very similar stuff is actually seen electronically, except electronically, the mobility seems to fall off for widths below 40 nanometers. So clearly, the difference is between the thermal regime and the electrical edge regime is that my timer?
No, but
okay, but might as well be. Yeah. I've got two slides. Yeah, I've got 2 slides I think of technical content. I'm done. Yeah. So again, the interesting difference in the physics is that the thermal conductivity falls off at larger scales. The electrical mobility falls off at smaller widths. Actually has to do with the phonon and electron mean-free path being different. The phonon mean-free path is actually longer. So you start seeing nanoscale effects in phonons before you see them in electrons, at least in graphene. I'm not going to describe this slide too much. Again, it's from the upcoming review paper. But we essentially look at these ballistic effects in a whole host of other 2D materials, distinguishing between where the ballistic regime is and where the diffusive regime is. And again, if I could just come up with a simple take-home message is that it's really, really probably not a good idea to use the bulk thermal properties in almost all submicron devices, right? Not just in graphene, but even in submicron devices not based on graphene. Even in MOS2, you probably ought to adjust the thermal conductivity for these quasi-ballistic effects. Not only that, but the cross-plane mean-free paths. So even in mean-free paths, cross-plane could actually be spanning, something like 20, 30 layers because the cross-plane mean-free paths are actually quite long as well. Okay, so just 2 words, not really technical slides on future outlook. We have a little NSF program, an NSF EFRI that's sort of built around these ideas. And so some of the ideas are, how do we exploit anisotropy? How do we, leverage this built-in thermoelectric cooling? Can we do something really wacky? By the way, this is what I showed right here is what I call a PowerPoint device, right? This is sort of a wishful thinking of some of the devices we could build, but we'll see if we can build them. And an example, something that we're trying to build right now is trying to build essentially a graphene MEMS device that leverages the flexibility of the material, but also leverages this high thermal conductivity. So it's essentially a thermal switch that could be used in some analogous way to an electrical switch, right? But for routing heat, obviously. Another thing that we're building right now is we're working with some battery experts who have taught us that if you jam lithium ions inside MOS2, you can actually control its thermal conductivity by a lot. So this is actually also a thermal switch. It's more of a thermal transistor because you can think of the lithium as sort of gating the heat flow, right? So lithium goes in, kind of slightly increases the separation of the MOS2 planes, and the cross-plane thermal conductivity of the material actually gets modulated by almost an order of magnitude, which is quite remarkable. It's not very fast, mind you. This is time scaled in minutes, right? But it's nevertheless, it's remarkable. You can't do this with silicon. I can't modulate the thermal conductivity of silicon by an order of magnitude and then, reversibly at all. At least I don't know how to do that. Okay. So just to summarize, some of the take-home messages are on 2D nanomaterials, especially 2D nanomaterials. Atomically thin, of course. Some of them are transparent. Most of them are flexible. High thermal conductivity for some, especially in plane, right? Low thermal conductivity for most of them, especially out of plane. Some high Seebeck coefficients, but there's a big asterisk there because the highest Seebeck coefficients are going to be at the lowest carrier density, so not necessarily in a useful regime for thermoelectrics. And then, I think there's a lot to be done with heterogeneous layering and really trying to understand the fundamental limitations of some of these things, as I'm sure you also saw in some of the previous talks. And so if you have other questions, I will take them right now, or I'll accept emails later. And I just want to thank some of the people that have helped me with material for this talk. Thank you.
Questions? So far the phonon repass is longer than Can you repeat the question?
Yeah, so the question was, why is the phonon mean-free path longer than the electron mean-free path? That's in graphene, by the way. That's only in graphene, and boron nitride probably. That's the way the math works out, basically. In MOS2, the phonon mean-free path is probably comparable to the electron mean-free path. But in graphene, the phonon group velocities are so large, the bonds are so strong that the phonons just propagate for huge distances before they scatter. I'm sorry, what's the question? What limits, the question is, what limits the mean-free path of phonons? Other phonons, so you have phonon-phonon scattering, scattering with a substrate. If you have suspended graphene, you don't have a substrate, but if you have graphene on a substrate, or MOS2 on a substrate for that matter, you have scattering with the substrate phonons as well. So you have phonon-phonon scattering with a substrate. Impurity scattering also limits it, of course, a little bit. But at room temperature and above, it's mostly phonon-phonon scattering. It's either with a substrate or the intrinsic phonons. Yeah?
Two questions. First, so about the velocity, right?
Yes.
So those are very nice measurements. Is the velocity saturation, have you looked at other materials? And I assume it's related to the optical phonon energy, but does it correlate with the optical phonon energy and effective mass?
Which velocity are we talking about? Sorry.
You had
Oh, yeah, drift velocity on suspended. Yeah.
near the start.
Yes. Yeah. This plot.
That's right. Yeah. So does it match up with optical phonon energy kind of theory?
It does.
I think
Yeah.
You might have
Yeah.
had that in your paper.
I did. Yeah. Yeah, we did. Yeah. So the question was, how does the drift velocity estimated here from suspended measurements match up with the theory, right? And is it truly limited by which phonons, right? Yeah, so the dashed line right here is the calculation based on the intrinsic optical phonons in graphene, right? So that's right. So this should be that. So this is about 3 × 10⁷, right? And so because we were struggling with lots and lots of samples and they were not really all the same, we said we're just going to take all the samples we made and put them in the paper. And so here's a measurement actually by sample number. And you can see that some of our probably our more disordered samples we're estimating only 10⁷. But from some of the better ones, with error bars and whatnot, we seem to be approaching what I think is the intrinsic limit for the material.
So non-uniformity can do that.
That's right. Yeah. Because these measurements are done at high field, high temperature on a suspended sample, and these are actually not pulsed. We've done some pulsed measurements as well, but these are not pulsed because there was not significant hysteresis here. So the pulse measurements are probably better if you have, I mean, they're obviously good if you have hysteresis. You're not going to be able to get rid of the thermal component in pulsed measurements because this is just too fast thermally. It's the heat will get out in less than a nanosecond, and there's just no way we can't do pulse measurements, right? So from a thermal point of view, these measurements are always steady state from a thermal point of view, right? But electrically, yes, if you have charge trapping, of course, pulse measurements will help.
Yeah, but I was thinking thermal, but you're right.
Right.
Okay, so maybe it's best to move on to our last talk. So let's thank Eric again.
Thank you.